Good afternoon, everybody. My name is Bryan from Dougherty Valley High School. And today, on behalf of my two other research members, Tanya Vidun from Valencia High School and Kayla Yuhani from Oaks Christian School, we are glad to present to you our research into morphological computation and soft robotics. We designed EarBloom, a bio-inspired intersection of high-fidelity hearing protection and fashion technology. To outline what we'll be discussing today, we'll start with introducing the issue we focused on and an overview of our solution. We'll then describe our design and testing process, which leads up to our final result and model. We'll follow that with some conclusions we reached by the end of our research project. Our world is full of so many sounds, from trains, cars, speakers, all kinds everywhere, whether it's in our ears or at a restaurant or at a store. High-risk professions include construction and music industries in which exposure to such loud sounds and noises occurs on a regular basis. Especially with the extent of audio digitization in our world today, we've become to listening to increasingly louder sounds on a regular basis, even starting at a young age. Noise pollution is here to stay. With the rate at which technology is advancing, and such loud noise can lead to damage on our hearing, and this starts at an extremely young age and develops over time, often leading to various degrees of hearing loss. We've decided to address the problem of hearing damage and noise pollution, but first turn to evaluating current hearing protection technologies. There are many limitations with the very common hearing technology protection applications today. Firstly, we have earplugs. The problem with earplugs is the improper fitting. This can lead to long-term health effects if they are led to be fitted improperly, as well as non-uniform attenuation and the earplugs not working properly if they're not fit in all the way. In addition to this, they are distorted along the 500 to 2000 hertz frequency range, meaning that they are not good for audio applications, as well as communication, like related activities such as talking to others. This same problem occurs in earmuffs. They still have the same distorted attenuation, but on top of that, they are heavy, and nobody wants to wear earmuffs in extremely hot construction climates. Finally, we have a new development in hearing protection technology known as high-fidelity hearing protection. These systems are often expensive if they are custom-made and can also be uncomfortable and lead to the same lasting health effects due to the extremely long tips that have to be wedged deep into the ear canal. So in order to address these limitations, today we ask the question, how can we apply morphological computation and soft robotics to target noise pollution, reduce hearing damage, and improve current hearing protection devices through the integration of fashion technology? Let's move on to some of the design process in early simulations. Our design is inspired by a concept called biomimicry, which is essentially taking inspirations from the natural world. Our design incorporates a type of flower, and the flower will bloom and close based off of the variable sound within the air. We took inspiration from the lily flower, where the edge of the lily flower will grow over the surface actuation and it will close up. This peacock feather design also is our fashion aspect. Essentially, the petals of the flower can also act as feathers of a peacock and create a fashionable incentive for people to wear hearing protection. Here are some of the early prototypes and design drawings. On the left-hand side, we have our initial EarBloom design with the dimensions of the petals as a 2D sketch. We took this over to Rhino 3D, a 3D modeling software, which allowed us to create a concept design for how the petals would bend inside, as well as create the initial model of EarBloom. This is a related work done by a research lab. In this research, they utilize conductive materials to create a bending and actuation motion. We hope to use this exact conductive material to create the same level of actuation within EarBloom. And here are some of the bend tests that we conducted in Rhino. The conductive material is placed at an anchor point or on the base of the pedal, And we concentrated the conductive material towards the middle or the top or the left and right to see how the figure would bend and react to this concentration of conductive material. We found that placing the concentration towards the middle created the most ergonomic and optimal bend, but there are also some other configurations which allowed good bending at different frequencies or different decibels of sound. And we will incorporate all of these in the results. To determine the optimal thickness of the pedal, we ran several static stress tests on a software called Fusion 360. This software allows us to run simulations of scenarios with different pedal thicknesses and how they'd respond under pressure from movement in all directions. The software enabled us to analyze the different options. Areas of red, orange, and yellow represented regions of greater stress. This means that the red, yellow, and orange regions are weaker when movement occurs, so we determined the 3 and 7 millimeter thicknesses had more thickness, but not as much strength, so we chose the 5 millimeter thickness as it would likely allow for greatest strength when the bending motion of the pedal occurs. We also decided to implement an emergency airbag system that would protect against extremely loud sounds of 140 decibels and louder. This would be continuous with the EarBloom device and is for one-time use only. As shown in the image, the portion labeled C is an automatically collapsible feature that inflates into the ear concha. It inflates through the ignition of sodium azide to produce nitrogen gas. This is the same system that is used in vehicle airbags as well. So we will be applying the immediate reaction of sodium azide into nitrogen gas into our inflatable to protect the entrance of the ear canal, which you can see to the image in the right. In terms of the sensors that we used a piezoelectric micro electromechanical system microphone, which essentially senses vibrations from sound and converts it into electrical current. If the sound is louder and has a greater amplitude, there will be stronger electric current with greater voltage. Based on the circuitry system that I'll elaborate on the next slide, if 85 decibels or 140 decibels is detected, specific outputs will occur based on the electric's current's voltage. It will actuate through electrical stimuli supplied by the battery. As shown in the image, this electric current will be able to propagate through EarBloom, which will allow the bending motion to occur since the electric field produced directs the device downwards. And here is a quick map of our control system. It starts with the sound vibrations that propagate through the air into the microphone. From there on, the microphone goes into the processing unit, which can detect either a threshold of a certain volume or detect if there's peak detection. From here, it will decide whether the sound is above 85 decibels or not. And if it is, then it will move on to the next two trees. If not, it will obviously go back into the microphone until the 85 decibel threshold is met. Then it decides whether it needs to activate the bending motion or the inflation. If it's above 110 decibels, then it will actuate the inflation mechanism to protect the ear concha. Otherwise, it will actuate the bending motion of the pedals, which closes up on the ear. We researched the different high fidelity mechanisms that are present within modern high fidelity hearing protection in order to preserve the sound quality and timbre of the incoming sounds. The problem is that acoustic absorption using a lot of these earplug materials naturally hampers the sound. And in order to resolve this problem, these mechanisms use the concept of resonance to add back the higher frequency sounds. There are two main designs for this. Firstly, the antenna design. The antenna design creates a high frequency vibration. In turn, this vibration is sent directly back into the ear, and this small filament that only vibrates in the high frequencies will boost the higher pitched sounds. The other design is the chamber design. The chambers resonate at a very high frequency, therefore increasing the resonant peak. This resonant peak within the sound attenuation will in turn return the higher pitched loss. And here's a detailed design of a single pedal. So from the front view, there is obviously the high fidelity cylindrical chamber, which is the design that we chose for our pedals. The pedal is made out of reticulated polyethylene foam, a type of acoustic material that absorbs sound better than common earplug foam. Towards the bottom of the pedal, there is the shell attachment, which is made out of silicone rubber. This silicone rubber can be molded and fitted to the ear for comfort. The conductive material is concentrated towards the top and the middle sections, and this will create the most optimal bend, which ergonomically fits over the ear. On the top right-hand side, we have a peacock design where the eye of the peacock is the high fidelity cylindrical chamber. Towards the cross section of the design, you can additionally see that the width of the pedal is this tiny chamber that will in turn produce better quality sound. And the surface of the pedal has the conductive material which will create the bending mechanism. Here are the results and analysis of the design. Here's an image of firstly what it will look like on the ear. As you can see, the many pedals that are not bended yet, but when a 85 decibels or higher sound is detected, the pedals bend towards the ear and cover the ear completely. This is an animation of what the design looks like. As you can see, the blue number is the decibel reading, and as the decibel readings increase, the pedals start to bend, and as soon as the 85 decibel threshold is met, the ear closes completely. And finally, let's wrap up what we discussed today. Today, we discussed the problem of hearing damage and noise pollution within the world of digitization. We discussed the concept of electrical stimuli to create a bending and inflating system. And in turn, we prototyped this system using computational design software. We provided a soft robotic solution and additional simulations to demonstrate how this would actually work in the real world. And finally, we provided a protective and fashionable design. And this design will, in hope, incentivize more people to utilize hearing protection. For our future work, we obviously plan to create a physical prototype of our simulations, but additional features that we could add are also more degrees of freedom. Hopefully these degrees of freedom can also create different ear shapes, and in turn, instead of working on only audio dampening, we can also work on audio amplification rather than attenuating the sound. We can also apply this method to additional senses. So exploring different senses in the body, not just hearing, maybe smell or some other sense. Here are some of the references that we used in our research. And we would like to acknowledge our instructors and our instructor TAs, Yin Yu, Dermot Flatley, and Alana Bartolini. We would also like to acknowledge and thank Dr. Lena Kim and UC Santa Barbara for allowing us to research this topic and giving us all the materials we needed to conduct this research. And thank you. This concludes our presentation on our research regarding EarBloom. You can contact us through these 3 emails. And thank you for listening to the presentation today once again. Thank you.